Hello and welcome. Here we are in lecture 12. So as you can see from the title slide, this will be the conclusion of our, 3-lecture functional programming primer. And so it'll be great. We're going to kind of wrap things up, as well as we're going to talk about something called pattern matching, which is a really nice feature available in Scala, which maybe you haven't seen in other languages, but it's actually a really, really strong feature. And so, yeah, it would be great to cover how we can use it. So let's get right to it. So in particular, today we're going to be talking about a couple more operators in functional programming: flat map, filter, some little kind of details, and then we'll get to write the pattern matching. So let's go ahead and load up our notebook. Great. Okay, so flat map, right? This might be better explained by first considering what happens if you try to call map on not just a collection, but a collection of collections. This can happen plenty of times, right? You're working with stuff, and the things you're working with, rather than being individual elements, they tend to be, each element is actually itself a collection. So for example, on the top of this diagram, you can see, I have a collection I'm working on, perhaps a seek or something, and each of those elements are they themselves seek. Fine, no problem. You can call map on that. And so when you call map on that, what you're getting is you're going to apply that map function to the elements of that collection. Just because those elements happen to they themselves be collections, no problem. That map function now needs to take in a collection, and when you make a map function, you can input type needs to match. You get to define the output type. In this example, the developer chose to have the output type also be a collection of some sort, but perhaps somehow could be a different type. And that's the point. Is so even though there may be many elements inside of here, this instance of this function is called once on this element, and this element happens to be a collection, right? And it produces, in this case, a collection. You can imagine maybe in some scenarios, perhaps you want to apply a function not just to this entire collection, but perhaps to every element inside one of these nested collections. In that case, you could call map, and then inside your function for that map, you could call map again, right? So you actually basically have two map calls, like a nested map call. That's fine. But either way, right, depending on what the output type of your map function is, you can end up with a collection of collections. Now, in many situations, that's what you intended. That's what you want. However, in some situations, maybe it's not what you want. So there's an operation in Scala that's very handy called flatten, right? And so what flatten does is if you have a collection of collections, it essentially merges them all together, right? So rather than having this kind of two-layer of nesting, you're going to get one layer of nesting. And so it's kind of realized that a very common pattern people will do is they would call map on some sort of collection, and then they would call flatten, right? And so you can put two and two together and do something called flat map, where even though maybe you're producing a collection with your function, rather than keeping that collection as a whole element, instead you append it to what's going on, right? And so you can see in this case, we are taking input collections in and going through. And so in this example, I've shown it as, oh yes, we have collections coming in, but it's actually not required, right? It is just required that this function produces a collection, and then you can append them together. And this is just one example, this instance of kind of combining map and flatten to get flat map. But flat map kind of can do other things as well. But conceptually, that's what you should be thinking about. It's, okay, I have a map-like operation, and I want to append a bunch of collection-like results. That's kind of what you should be thinking, right? Now, maybe we should go ahead and look at some examples, right? So let's say, for example, we have a simple collection, and what are we going to do with it? Well, let's see. Okay, if there's always decided to go fill things in, right? So if, for example, we wanted to fill in a seek, we can do that. So maybe I'll go ahead and comment these out so they won't be distracting. Those are just kind of reminders of how this code works. But let's, for example, let's say I want to call seek.fill on a number, right? So, well, I'm going to get I copies of the value I, right? And if I do that on 0 through 5, well, I get 0 zeros, 1 1, 2 2s, 3 3s, and 4 4s. Okay, that's cool. Now, you can see in this case, here's the two levels of collections, right? I have an outer vector, and then inside that I have these lists, right? Now, if I was to call .flatten, it would kind of remove those inner wrappers of the list, and that would have a single collection, right? Alternatively, rather than calling map in .flatten, I could call flat map. And that's what you're seeing down there. Yeah, this is a flat map. It's going to be helpful for other scenarios as well. So here we're using it specifically on collections where you have many elements. Another scenario this kind of stuff comes up, but sometimes you might want to be clever about how you deal with options and things like that. That'll be at the end of today's lecture, perhaps a future lecture. But for now, you can think of it as just kind of another more powerful way of kind of working with these collections of collections and how to kind of handle that. So I'm going to pause here for any questions so far. Okay, so that's flat map. For some of these functional operators, especially today, they're getting kind of more sophisticated cases. When you think about how they will be used inside your hardware generators in Chisel, I've kind of encouraged this emphasis on, sometimes being a little bit judicious with advanced features in case it really improves your code otherwise, makes it harder to read or whatever, maybe being cautious. Flat map may be one you may not use a ton in your Chisel generator, but it's one of these things that's very helpful to be aware of. You will see if you read Scala code. You also may use it in the Scala code you write. So we talked about in our testing lecture how you don't necessarily just write Chisel to make a hardware generator. You may also write Scala to perhaps model the functional behavior you want of your design for verifying and testing it. You also need to write quite a bit of Scala code to kind of create that harness and testing infrastructure to interface your model with your design. And so for those kind of situations, flat map becomes extremely useful. So that's why we're kind of covering this. Even though in your hardware design, maybe you're trying to keep it super readable in your generator, maybe you won't use it. The odds you'll see it or use it within your Scala models or your harnessing infrastructure is quite high. Another functional operator, which is pretty handy, is filter, right? So what does it do? Well, given a function, if the function returns true, it's going to keep the elements that match that function. And if they are false, it'll drop them. So technically, that kind of function is called a predicate. And you can see it's given a single element, and it's going to return if it's true or false. And like I said, if it's true, filter keeps it. If it's false, it's going to drop it. So let's say, for example, we define a function is even. And you can see it, of course, returns a Boolean, and it sees, is it divisible by 2? And so given that, we can go ahead and, filter. So given this range L, we can apply a filter, and well, guess what? Those are even numbers, including 0, because we, define it that way. Now, let's say, for example, maybe you have a predicate and you want to do not the predicate. Now, one way you could do it is maybe you might say, oh, I'll write the function out, and I'll just say not, right? That seems like an okay thing to do. Okay, totally functionally correct. Once again, Scala has, these a lot of things built in. So, for example, there's a filter not. And so, yeah, you can see it's going to return the ones that get false from this predicate. In other words, 1 and 3. And so once again, if these kinds of, little tricks maybe aren't super intuitive, you don't know to look for these. Like I said, at some point, please go by the course homepage under references section under Scala. There's a link to, like I said, Pavel's blog. And Pavel, it's a very long blog post. So maybe you kind of scroll through it time to time. He'll list a lot of these kinds of things. Like, did you know Scala has this? Did you know Scala has that? And in most cases, he's showing something where it's perfectly functionally correct Scala code. And it's just showing people to be aware of there's some, built-in nicety in the language they may not have been aware of. And so filter not is kind of one of those things. Interestingly, there's also 2 other operations. There's for all and exists. So these are a little different, right? So filter is kind of like almost in some ways like a map, right? You apply a function to every element and you get an output collection. It's not maybe quite like map. It's maybe more like flat map in the sense that sometimes the function will return something, sometimes the function will return nothing, and you're going to kind of compress it out. Before I forget, that's actually a great reminder. I should go back to this. There is no requirement the number of input elements to one of these collections match the number of output elements with flat map, right? So you could have a single element coming in and it producing many elements. You could have many elements coming in and returning 0 elements. That's totally fine with flat map. So for example, if you have something where you expect to, change the number of elements and you want to maybe drop or add things, and that's why you want to kind of aggregate them all together, another good use for flat map. Okay, sorry for that. A reminder to go back to that. But talking about some of these other things available to us, we have both for all and exists. So what for all is going to do is rather than returning collection, it's going to return a Boolean, and it's going to apply your predicate to every single element, right? And if it's true for every single one, this thing is true. And if any single one of them is not past that predicate, then it's going to say false, right? And meanwhile, exists is kind of the other one. So exists is going to apply your predicate to every element, and if any one of them is true, it's going to say true. So let's look at these two operations. In some ways, they're kind of very similar to that thing we were talking about this last week about these chisel reductions that are these bitwise reductions. Remember we said there was an OR reduction, as apply every bit OR to every bit and combine them all. That's basically exists, right? Or if any one of those is true, the whole thing is true. It's only false if they're all false. So yeah, the only way this is going to be false is if there does not exist, right? Likewise, for all, it's kind of like an and reduction, right? Where if it's true for every single one of these and you're all ending them together, great. If not, there you have it. So you can see, for example, hey, if I grab these elements, are they all even? No. Is there one within there that is even? Yes. Cool. And you can imagine if you were trying to write this on your own, how it might look, right? Maybe if you did with functional programming, maybe do some sort of, fold left or something, and, kind of retaining a residual, like, is it, true or not true? And then you might say, oh, wait, that's not great because, depending on finding a certain outcome, maybe I want to terminate early. Maybe I'll write this like a for loop in a var or something. Hey, it's all in the language. Don't worry about it. So yeah, you can use for all and exist. These are library functions that are kind of handy and easy to use. Cool. I'll pause for any more questions. Okay, so then if you want to think about what a filter looks like, as you can see, it applies this function to every element. For ones that are true, it gets passed on, and for ones that are not true, they're just dropped, right? And so you can see this output collection will be at most as large as this, perhaps smaller. Things don't pass the filter. And remember, flat map's kind of a more general, more powerful operation. So flat map, you can kind of almost do anything with it, or not anything, but a lot of things with it, and you can kind of use flat map to kind of mimic other operators. So of course, you can use flat map to mimic map. You can use flat map to do a filter by kind of, returning collections of size 0, right? And so it's nice when, something matches a special case to not just use flat map, but instead use a specific thing you're doing. You should actually use map if it's a map. You should actually use filter if it's a filter. But we covered flat map earlier. Some Scala programmers use it for everything kind of as always all the time, but I would recommend if it matches one of these other patterns to use the other operator. Cool. Okay, so let's go ahead and put this filter to work and kind of do a little bit of an interesting program. And this is a problem I'm sure you can solve. You can solve it more efficiently perhaps, but it's kind of fun to see how concise this is with this code and appreciate how you can kind of use functional programming to build this up. So what we're going to do is we're going to enumerate, list out all the primes, let's say in this case up to 100. So how might we go about doing that? Well, you normally, if you want to see if the number is prime, of course, to see if it's divisible by any other primes. And so there's something called a prime sieve. You may have seen this in a math class, where what you do is you, this is the, very old algorithm, you find a prime, and then you remove all multiples of that from consideration. So for example, starting with 2, okay, let's say I'm trying to find all the primes between, 2 and 100. Well, if I know 2 is prime, and I decide 2 is prime, I go ahead and remove every number from the list of remaining numbers that is divisible by 2. So I'm going to go ahead and remove 2, 4, 6, 8. I'm going to go ahead and remove all those numbers. So now after I've done 2, there's a multiple of 2 left in that thing. And let's say next I see, 3 is the next head of that list. Well, I'll go ahead and call 3 prime and then remove every multiple of 3. So I'm going to remove 3, 6, 9, 12, etc. And 6 is already removed by 2, but if it wasn't removed, it'll be removed now. And you can see this kind of algorithm works, where it's going to kind of take the least number in this collection, declare that prime, and then remove all multiples of that in the remainder, right? So how are we going to go about building this? Well, we're going to kind of build this up using functional programming. So we're actually going to build this multiple of function. And we can see we're using that technique we talked about last time of currying. So we have 2 argument lists here, right? So what are we doing? Well, what we're trying to see is, be a multiple of A, right? That is, can A evenly divide B? That's what it is, going to return a Boolean result. And so how are we going to use that? Well, we have this function called remove x. So it's going to do is, given a collection of numbers, it's going to remove all multiples of x, right? So how does that work? Well, it's going to go through L, apply a filter, and it's going to apply the multiple of this, right? So let's kind of go through this piece by piece, right? So remember, this is a curried function. So if we apply one argument to it, it's going to produce a function that's going to still require an additional argument to operate, right? And that's kind of what we're going to get. So we're going to say, hey, I want to make a special version of this multiple of function specialized for x. In this case, whatever x is when I first run it. And then I'm going to apply that function to every element in this collection L, right? In particular, when it's true, I'm actually going to drop it. And when it's false, I'm going to keep it. And the reason why is I'm using filter not. Now, this was a programmer design choice. You're right, I could, of course, use filter and made this not equal up here. But it's sometimes easier to kind of keep track of it that way. And I thought, multiple of is a very clear, kind of thing to kind of talk about. And maybe I should, for example, maybe rename this, remove multiples of x to be extra clear, right? And then we can go ahead and do that. Right. Okay. So, going on, I saw there was a question in chat saying, what's the convention? How do I know when I do multiple of x and I have, there's multiple argument lists and I only give one of them, which one am I getting? It goes left to right. So if I call multiple of like this, if only one param, it's supplying this to the A. And so then by calling multiple of like this, I've already, have a function now that this param list is gone, right? It's already been applied. A has already been substituted in here, so we really have a function that just takes in a single additional argument and just returns a Boolean, right? And so that's what we need for this predicate, right? We need a predicate that takes in a single integer and returns a Boolean. Originally multiple of required two integers, so that was inappropriate. But by supplying one of them with currying, it's able to kind of pull that in and create this function now that takes in only one more integer, and then we're set. Good question. So go ahead and run this real quick. Yeah, we kind of see some stuff. We're defining some functions. Here's the range. But when we go ahead and, see what happens, right? So, for example, these two lines are equivalent, right? So basically what we're doing is, hey, I take all my nums and, filter them if they're multiples of 5. See, 2, 3, 4, no 5, right? No 10. We're removing those parts. And so here we're kind of doing it manually, versus we could have, of course, used our handy function and just done it, right? And we're going to get the same result. Okay, so we removed all multiples of 5. Now, if we want to do this as a sieve and actually find all the primes, what are we going to do? We are going to do a couple things. Well, so we're going to call sieve on this list. And what it's going to do is, of course, if we ever come across the base case, if the list is empty, well, then we're done. Then when we're iterating, you may have seen this before, and it's worth covering again for seeks. If you want to kind of iterate recursively, it's often nice to kind of grab the head element, and then the remainder of the head, so everything after the head is the tails, right? So this is one element. This is a collection, potentially empty, if it's, down to the last element. Okay, so yeah, if it's empty, I'm done. But if it's not done, well, I'll take the first element off and say, you know what? Nobody else has removed this number, so it must be prime. And then I'm going to recursively call, myself and remove, not just on the same data, but remove all multiples of myself, right? So basically saying, hey, you know what? I'm declaring myself prime, so I'm going to remove all multiples of myself from the remainder of these numbers, right? If we go ahead and run this, hopefully these numbers look familiar as, the primes from up to 100, right? You can see, 2, 3, 5, 7, 11, 13. So this is pretty cool. So in the end of the day, we've actually kind of, in 5 lines, 6 lines, I guess, built up a little function here to kind of count up these primes, right? It's kind of a nice example of us seeing few things that work here, right? We have not only our, filtering with predicates, we're using currying to kind of, almost like a function generator, right? We're kind of building a function, use it as we need it, and it's kind of running through it. This is, of course, an artificial example in Scala, but you can imagine how sometimes something like this is pretty handy and helpful for maybe generating test cases, if you're trying to, really explore a lot of combinations or whatever. This is where it's perhaps most useful. Cool. I'll pause for any additional questions. Okay. So here we are using filter to kind of build a prime sieve. That's pretty neat. This one we covered in kind of in passing. I made a deliberate slide to kind of make sure you're aware of it. That, for common reductions, you can just call .sum, .product, .min, .max. They're built in. It's very handy. And so, yeah, we saw this kind of previously in the reduction lecture, but here I'm just kind of reminding you that, yes, these all exist. They may not exist in some of the Chisel collections, but that's the Chisel developers issue rather than something. This is available for all the Scala collections. And so when people talk about Scala, they often talk about the strength for the standard library, and really the Scala standard library strength is its collections. The collections aren't just data structures, they actually have an amazing array of, operations built onto them already available for you, and you can kind of compose functions pretty quickly. Yeah, so as we mentioned, some of this wonderfulness of the Scala collections isn't all available in Chisel. Perhaps we'll get inspired and contribute some of this back upstream, or etc. Cool. So now we're gonna crank this to like 11 or 12, whatever you want to call it. We're going to use our functional programming constructs to do matrix multiplication, right? And the reason why we're doing this is, of course, there should be a library or something to call do matrix multiplication, but as an example of kind of a lot of elements swirling around, right? If you go back to your algorithms memory, for now we can assume these matrices are square. Okay, so given, a square matrix, let's say it's n elements in one dimension. I have, n squared elements in a matrix. And when I multiply two matrices, it's going to be n cubed operations, right? It's kind of basic multiplication for matrices, not one of these advanced algorithms. Okay, so why is it n cubed? Well, for each one of those n squared elements in the output, I'm actually going to multiply an entire row by an entire column, like a dot product, right? And so it's n operations, right? So n operations times n squared elements, we get n cubed, right? And so it's kind of about this matrix multiplication example. This is a collect example of, a lot of different element accesses and collection exchanges, right? And so let's talk our way through how we're going to do this. Now, eventually you might write this as, 3 nested for loops. Fine, right? But for today, we're going to try and do it with functional programming. So how are we going to do that? Well, first, let's go ahead and make a matrix. So how are we going to make a matrix? We're going to actually use seek.tabulate. And interestingly, before we've done tabulate, we've only given it a single number. If you actually give it multiple dimensions, it actually will create a multi-dimensional seek. So it'll be a seek of seeks, in this case, 4x4. And just to have some data to populate this, we said, let's just add up the indices. So, because it's a two-dimensional seek, when you call .tabulate, that function here needs to take in two arguments. So we're going to say, hey, we'll take these as two coordinates I and j, and we'll just add them up to get numbers in there, right? So you can imagine this matrix to be, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Cool. Maybe it's best if I go ahead and just run some stuff in the beginning, right? So you can see, for example, there is our matrix, and you can see there it is. Cool. Now, if I want to grab a row of this matrix, well, it's just as simple as, giving a argument to Matt, and that'll give me a seek, right? That's going to be the row. Because basically this layout we're having here is row major, right? This is, row 0. This is row 1. It's basically a row major layout. Now, if I want to grab a column, I want to somehow grab, vertically, right? Which is grabbing an element from multiple collections, right? So how are we going to do that? Well, we actually can apply map to our matrix. So the map's going to be given each one of these entire seeks. And then within each one of those entire seeks, we're going to go ahead and grab the element, right? So perhaps you want to be more verbose rather than using that placeholder syntax. You might say, hey, given a row, I'm going to go ahead and grab an element within that row, right? So for a given, let's say I want index, 1, well, it's going to apply a map, and each one of these maps is going to map this function onto each one of these seeks, and each one of these seeks, well, I'm going to say, hey, I want element 1, element 1, element 1, element 1. And so if we go ahead and run this, we can see, yes, it can successfully run this grab column, right? So it's kind of a cool example of these functional programming operators at work. Great. So already now we have this matrix we kind of built up, just using this 2D seeks already built into the language. Grabbing a row is easy. To grab a column, we're going to go ahead and, just write this little function we just did. So now let's say we need to do a dot product at some point, right? Well, what's a dot product going to be? Well, we're going to have two vectors, right? In this case, seeks, and we're going to multiply all the elements together and then add them up. So to accomplish that, we have these two collections using functional programming. We're going to go ahead and zip them together. So we had two collections. Now we have one collection where the elements are pairs, where each pair is an element from A and B. And for each one of those things, we're going to, of course, for each one of those tuples out of those pairs, we're going to go ahead and pull them out, extract them from the tuple, multiply them, right, get that product, and then, so the result of this is going to be, the products of all those elements in those vectors, right, and then we're going to go ahead and add them up for the final thing for the dot product. Cool. And so, great. Let me pause for any questions so far. Yes, this is getting a little bit, more detailed. This is probably like the most sophisticated code example we have this quarter, so don't worry if this is a little heavy. But, it's working so far. Alrighty, so now if I actually try to do matrix multiplication, right, our matrix type's basically a 2D seek, a seek of seeks, right? So you can see that type signature right here. So now if I'm going to multiply these, what am I going to do? Well, what I'm going to do is I'm going to take in each one of the matrices, right, and apply map to it. So remember kind of original structure. Each one of these elements we're getting back is actually going to be a seek of itself, right? In particular, these are going to be rows of A, right? So I even had a very verbose variable name here. Okay, rows of A. And actually, if what we're going to want to do is functional programming, we are going to map on these individual elements within each row. And when we do that, we actually want to know what our index is, right? So we're going to go ahead and call zip with index. Here's an example of that being used. And once again, we're going to get tuples out of that. To match on those tuples, we use that case keyword. We're going to get the element of the row originally, and then, of course, the index that was created by zip with index. Okay, so now to compute a given element in our output matrix, remember it's the result of a dot product. You take the row of A and the dot product, and compute the dot product out with the column of B, right? And so we already have the row of A available to us, right? That's a variable we kind of already bound, right? And then the column of B, well, because we zip with index, we know what column we're at. And we can go ahead and, extract that column from B. That's what grab call is going to do. So now we have the column of B, right? And so, okay, row of A, dot product column of B, that's going to be the result for this element of the matrix. And so, yeah, this is going to do the right thing. If we, for example, square the matrix we were given, this is what we get. Maybe we can sanity check just the easiest, smallest row. Okay, 14. Okay, so that'll be 0, 1, 2, 3, dot product with 0, 1, 2, 3. So 0 plus 1 plus 4 plus 9. Yeah, that's 14. Okay, at least one element's right. So there we go. Like I said, this isn't super intuitive and happy. That's fine. Maybe you'd be happier with a for loop. Very okay. We're just trying to have fun with this course, try out functional programming, see what we can do with it, see if we can push things a little bit. Sometimes maybe we can go too far and we can decide maybe it would be more clear, more easy to maintain to do something like a for loop, right? But just kind of, thinking about what's possible with these collections, these abstractions, these functional operators. Here we are kind of demonstrating it. And interestingly, we actually can perhaps do this more concisely using the tabulate feature. So let's kind of see how that might look, right? So how might that look? Well, another way of thinking about this is kind of a very input-centric way of thinking about the problem. Alternatively, you can think of it as very output-centric, right? So this is kind of going through every element of the input matrix and then kind of, mapping it through. And this works fine if matrix is squared. Matrix is not squared. This is maybe not going to be quite the right thing. If we do it differently, let's go ahead and use that tabulate functionality in Seek, right? So remember, tabulate is going to create a new Seek. You tell it the dimensions you want, and it's going to, create a, and it's going to apply this function to all its elements, right? So in this case, I'm going to say, hey, give me a matrix of these dimensions, and, just the outer dimensions, we do the matrix product, right? So it's going to be the row size of A and the number of rows in B, or say number of calls and the number of rows. But the result is, okay, so given these, coordinates in our future output matrix, what does it represent? Well, it represents the dot product of the row of A and the column of B. So perhaps maybe it's a more easy to understand, where you wrap your head around what kind of we're writing this, but yeah, we get the same result, and then a way of kind of computing it. And yeah, like I said, I imagine for square matrices, they're all totally equivalent, but for how these handle non-square matrices, a little bit of a wrinkle. And as always, of course, if it's a matrix multiplication, you should use built-in library functions when available, but here we are kind of, playing with it on our own and trying things out. Cool, I'm gonna pause for any questions. Great, so yeah, here's a pretty involved functional programming example, really kind of just trying to crank it despite all the craziness of all these operators. Remember that, we didn't change A or B, and really we're kind of, on the fly creating new references and values and passing those through, right? Rather than actually using a lot of mutable state or anything. Okay, so then let's jump into pattern matching. So what's interesting about pattern matching is kind of how versatile it is in the language and how much it appears everywhere. So it turns out, actually, using that case keyword, you were invoking this whether you knew it or not. So even on this prior slide, when we were trying to grab out the portions of a tuple, we were telling the language to pattern match. Hey, I think you're looking at a tuple that has two elements, and I want to give them these names. And then the language says, oh yeah, guess what? On the other end, there was a tuple, and I do know it, and now I can go ahead and bind those names for you. It's kind of nice. It can kind of do that for us. And so it can do a lot of stuff. So pattern matching is pretty sophisticated. I'm going to kind of show multiple ways of using it, multiple ways it kind of reappears. But understand it's a very versatile construct that kind of is used throughout the language, right? So at the simplest sense, we can kind of use this instead of if, else, or switch it, right? So for example, if I have some sort of value and I want to pattern match on that value, well, I can go to what's called a match block and say, hey, I want to match, and then, delineate my cases. And then for, this case, the thing that's going to cause it to match, and then what you're supposed to do with it, right? Okay, so for example, if this is 0, we're going to return the string 0. If it's, we can see if you're in a case, right? For example, okay, what if it's, 1? Well, we're going to see it's going to return the string not, right? And so actually, not only can it match like a single element, you can of course do the single bar for an or, right? And so it's going to match 1 or 3 that way. Cool. What's also interesting is that you can also put an if in line, right? So I can have some condition here. In this case, I actually didn't put a constant here. I put a variable. So it's going to bind. It's going to bind this thing here. Maybe I should perhaps make this extra clear. Perhaps rename that thing. So okay, so it's going to bind it to y, and then hey, if y is even, if this is true, it's going to match this. If it's not true, it's going to go on to the next case, right? So if I go ahead and make this, 4, it's going to be, even. Cool. And if it's 5, well, it's not going to pass that even test. It's actually going to match this other string and be founded. Cool. And you also can use the placeholder. In this case, it's not so much a placeholder. It's actually just the default case, right? So I can say, this is your fallout, and it says, hey, other. So this is kind of using it just as kind of a supercharged switch statement, which is actually a common use of it. Here you're doing it on like a literal number, right? But you'll often do it in more sophisticated types, and we'll see that in just a second. This is kind of just demonstrating the various things, right? You can match on a value. You can put ors in there. You can even do an if inline right here. And you can also have a default base case. And so one cool example of how to use pattern matching is actually for case classes. So remember these from before, we kind of said, hey, they're really handy in Chisel, the kind of way to package up parameters as a minimum. Use them for a lot of things, right? And so what's kind of fun about them is you can go ahead and match on case classes very nicely. And that's what's cool about case classes, not only to have all these other features, one of the features they have is a pattern match well. So we have this kind of, arbitrary example where let's say we assign, we're going to have these case classes that represent vehicles of some sort, right? So to kind of unite them, we're going to call them all the same abstract class, and they're all going to extend it. We'll come back to inheritance later this quarter, but for now, you can just say that's kind of a little boilerplate. But within these vehicles, we're going to say, hey, you know what? We have a helicopter or a submarine, right? And we can say what color they are and who's driving it. And to go ahead and have a collection of these people, we'll say, hey, you know what? Let's say we have, a helicopter that's gray, being driven by Marta, a helicopter that's blue, being driven by Laura, and a submarine that's yellow, being driven by Paul. Okay. So given these things, we can go ahead and use pattern matching on them, right? So we can match on the type of the case class. Say, hey, you know what? If you give me a helicopter, now we know it's a helicopter. So at this point, when I use it in this portion, the type of H is a helicopter. It's no longer just an abstract vehicle, it's helicopter. So I can go ahead and call like .color and, say it's a helicopter. I, of course, can match a summary and do that. And so if we go ahead and run that portion of the code, right, we'll see, for example, that this is the result of running this first for each across it, right? So this is a for each because the output of what we're doing is just a print line, so we're not really producing anything. We care about the side effect, and that, of course, is the side effect to our console. And yeah, okay, we identify the helicopters and summaries within the stuff. Now, you're going to kind of start showing some more sophisticated pattern matching examples, right? What if I want helicopters that are blue? And then what's also interesting is, you know what? This is a variable. This is not something it's matching. This is something that's just binding. So matching kind of go either ways. In this case, it's matching helicopters that are blue. In this case, it's saying, you know what? This is, now bound as a driver. So if this portion matches, now I can say I have driver, and I can just say so-and-so is a blue helicopter, which, yes, Laura has a blue helicopter. Here we have, once again, kind of, we're going to match on a submarine, no problem. And so you can kind of see this. It's actually pretty cool. You actually can have some cases in here. Maybe we'll go ahead and make this more specific and say, if, let's say S dot, color, is yellow. I don't want to hear about it unless it's yellow. Yeah, that's Paul's yellow submarine, right? And you know what? If I say I don't care about yellow submarines, then that goes away, right? So this is pretty cool. So we can kind of interoperate our types here and kind of do some pretty cool matching. So you can imagine here we're doing a match, right? But you can imagine this is not far away from being used inside of a map function, inside of a flat map function, inside of a for each function. There's kind of a lot of ways you can apply this, right? You can kind of really crank this to 11. Additionally, just kind of looking at the top part here. Okay, so I ran for each on movers, so I'm going to be iterating through this collection. So there's V, and for each one is V's. We're going to go ahead and call match on it. We can kind of just compact this out and go straight to the placeholder syntax, right? That's what we did there. We also have this, base case. Maybe we'll even make this more clear and say, print line, didn't match, right? And so hey, you know what? One of these things didn't match. So cool. So this is pretty handy, right? You can, match on the whole type. You can set some of the fields. You can apply your if predicates here and kind of, filter things down. So sometimes when you really kind of do a lot of stuff, you really kind of want to zoom in the data you want. This is super, super helpful. I'm not covering this course, but there's other operations like collect in the language will also let you kind of really zoom in on the data you want inside of a collection. So it's kind of fun about Scala is you really can kind of be very productive, right? You can use these language constructs and really get what you want to very quickly, and sometimes very little characters, but also not just a few characters, actually taking advantage of recognizing common patterns how people use things and putting those into language, and thus when someone's familiar with those common patterns, they also can read your code quickly and understand what you're doing quickly. Cool. So before I go on, I'm going to pause for any more questions. The next set's going to be kind of us being a little more graceful of how we deal with option. Okay, so for dealing with option, we're going to do a few things, right? So first, let's get some options in the first place. So we're going to go ahead and, populate this the seek, and we're going to say, give me all the numbers 0, 1, 2, 3, 4, and you know what? If they're odd, we'll say it's a number, and if it's even, we'll say it's a none, right? So, what do we get? Well, we have, this list, and you can see because of the way it's been constructed, there's some nuns intermixed with some sums, right? Some numbers that actually exist. So the way we kind of covered options so far in this course is at a minimum, you need options to do things like having optional ports in the bundle. And as you saw in the homework, we also kind of use option to, a valid, which is kind of, the hardware equivalent of an option to kind of indicate something is there. And so there's other ways to kind of work with option, right? So you actually are handed options, we're actually trying to deal with options in a graceful manner. We've had all this work with, is defined and .get. But, sometimes it's kind of very verbose. Depending on what your code is trying to do, sometimes you actually do want to filter out and not do anything if it's not defined. Other times, a default value is totally fine. So in cases where default value is totally fine, if it's going to be none, you can kind of go through it, right? For example, if I say, hey, give me 0, right? Well, 0 was a none. So it's a none, so it can't get it. So I'm getting the or else, right? But if I ask for element 1, right? Element 1 is a sum of value 1, so that's what I get, right? So get or else is one kind of handy way to work with an option. Alternatively, as you kind of talked about, kind of verbose ways to, use defined and do .get. And as clunky as this might seem, it gets the job done, right? A lot of times you kind of can filter out, the operations you want to do or not do. And, you should only be calling .get when you've already kind of checked it exists. And if you're going through it, right? If there's any chance that .get's not going to work out, you should either call is defined or get or else, right? Because if you call .get and it fails, then you're going to get an exception and etc. What's interesting, though, is that we can kind of count on the functional programming features of Scala kind of filtering out nuns for us in a way, right? So, for example, if I say for each print line on 1, I'm getting 1. So what's happening, right? So it is going through, and maybe it's better if I actually go ahead and just run it on all of L. So you run all of L for each one of those elements is calling print line. Now, the reason why is in that case, the functional programming operator is being applied at the seek level, right? So at the seek level, it's going to go through and then apply the function print line to every element, right? And so every element is an option, and so it's either a none or a sum. Now, if I go ahead and instead access an element of that collection, now I have a single element, it's a type option. And if I now apply for each to that, and so I'm applying for each to an option, right? So it's not a collection that has many, many elements, it's an option, right? So an option is, in some ways you can kind of think of it as like a special collection that has either 0 or 1 elements, right? So when I say, it's a none, it's kind of like it's empty, right? And when it's a sum, it's kind of like it has exactly 1 element, right? And so when I access index 1, what I've done is I said, okay, give me the element 1. whatever it is, whether it's a none or a sum, and I'm going to try to call for each print line on it, right? And so if there's something there, then yes, I can print it. Now, if there's not something there, it's not going to do anything, right? Because it's basically like trying to run a functional programming operator on an empty collection. Now, what's interesting is earlier I kind of mentioned the stop flatten operation. So you think of options kind of like a collection that's, of at most size 1, perhaps size 0 if it's empty. A seek of options is kind of almost like a collection of collections, right? Where the element type is option, so that, like I said, option is kind of like at most a collection of size 1, so it's kind of like a collection of collections. So thus, if I was to call flatten, I want to get rid of that innermost kind of collection, or that next layer down level of collection aggregation. And guess what? I'm appending, options with nuns, options together, and, sums that are sums will persist, and ones that are nuns are kind of squished together, right? And so, yeah, you can see that when I call it on l.flatten, now I've squished those out, right? So those nuns got squished out. Cool. And so that's kind of neat. So in some ways you can kind of see how this kind of all fits together, right? So options kind of this really nice feature where we have the ability to kind of indicate something existing or not existing without needing to encroach on the expressibility of that particular value. But we also can kind of think of it conceptually like a collection, of up to size 1, perhaps it's empty, it's only size 0, and we can do things like .flatten on it, or you can do flat map on it. Or you can use your pattern matching on it, which we're going to do right down here, right? So if we're doing the pattern matching, for example, we're going to go through each element, and we can say, I can match, is it sum or none, right? So you can pattern match with your options. And this is a great example of that, right? Here we're saying, I don't just want the fact that it's a type sum, I want to know, I want to bind this I to the contents of that sum, right? And so, yeah, you can see, for example, when it's not able to match, we're going to say it was empty. And I believe if I do this, it might also still work. Nope, never mind. I didn't handle this right. There's some cases in Scala we can do what's called a partial function, and it'll be just fine. I believe if I actually called collect on that variant, it would work, but it's a little weird to do collect with print line. Yeah, it's a little weird because collect's not about the side effects, collect's about the result, and the result in this case is print line is going to be returning empty things. But that's a little detail. Cool. So yeah, here's some more examples of kind of, putting it all together. And you kind of see now the bigger picture, right? All these things we've been covering, they all kind of fit together, right? And the result is that after, becoming familiar with these operations, you should feel pretty proficient at kind of having collections of numbers or whatever type you have and be able to kind of, apply these kind of common patterns to them, right? If I need to have a collection of things, I need to map them all, or I want to do some sort of side effect from all of them, maybe for each, right? Or maybe I want to combine them in some way for reduce, or maybe I want to combine them in a very deliberate way with fold left. Or maybe I want to kind of have collections of collections and do things with flat map or flatten. Or, as we saw today, also be able to do things with pattern matching and options. So this is a pretty rich set of stuff in the language, right? We really kind of covered a lot of Scala. Scala is a very feature-rich language. You've already learned enough to, do some pretty cool stuff with it. In terms of what's remaining for us to cover in this language, there's stuff like it's very sophisticated object-oriented system and all that kind of stuff. We'll get to that eventually. But that was kind of the point. This last 3 lecture sequence kind of give you a little bit of sense of this functional programming. I think, in terms of what's going to go inside of your generators, I would expect, lectures 1 and 2, using map and reduce are kind of things you're commonly going to want to do inside a hardware generator. But some stuff we saw today is kind of just a little bit of, additional background for your own knowledge, and perhaps you might find it useful things like in your test case generators and how you want to, explore certain design spaces. Or perhaps inside your Scala model, right? Maybe you can mimic the functionality you're trying to do in hardware and a very tight 6 lines of Scala. Maybe you do that, in 30 or 40 lines in your generator in Chisel because you're trying to be very deliberate and do things a certain way, but perhaps this helps. And so here's kind of a quick thing. Hopefully you have some fun kind of trying things out and playing with it. Cool. So I'll pause for any last questions. Cool. Okay. I also did want to follow up from last Friday where we were asked about how Chisel implemented the delay register because this function .iterate, and I was like, oh wait, that's going to be defined on a seek. and it wasn't defined on a .seek. And then some further investigation, as I kind of shared on Slack, I'll put this in the recording, indicated that actually .iterate was something proposed within the within the Chisel ecosystem, right? And so let's talk briefly about what was going on there, right? So .iterate was being called on a seek, and yet .iterate was not defined on seeks, right? So it's not originally defined by Scala.seeks, right? So it's possible in Scala something called a mixin, we're able to kind of inject additional things onto it. The particular case with the .iterate was a little bit more complicated than average. And this is something that's a little bit more sophisticated, is that Scala has this macro system. And you may be wondering, why the heck are we talking about macros? In order to make the language look a little bit less like a library and a little bit more like its own language, more and more functionality in Chisel has been pulled from, regular Scala libraries and more into Scala macros. And the reason why is by kind of, doing some stuff in the macro level early on, this kind of pre-processing stage, they're able sometimes to give much better error messages and to kind of detect things better. All that being said, in this particular case of a delay register, of a shift register, I'm actually kind of curious as to why that was done with this sophisticated, macro rather than a more conventional approach. Perhaps this is a question we can ask a Chisel developer, which hopefully we'll have one of them come by for a guest lecture later this quarter. But that was kind of a quick follow-up for that little detail. But yeah, so the answer is .iterate is not a Scala operation. That was something defined within the Chisel world. That's one of the disadvantages of kind of browsing code through like a web page browser is, of course, you're like, where does this come from? That's one of those things, if we were looking at this in the IDE, we could easily just, right-click and say, hey, go to implementation. We could have had this perhaps answered in 30 seconds during the lecture. And instead of looking at, a web page during a lecture and then trying to search, and it was slow. So as soon as the lecture ended, I, of course, fired up IntelliJ and found this out much quicker. But now we all know. Cool. Great. Well, I think that's it for today. Have a good day, folks.